Close your eyes if you feel comfortable. Let your mind drift into the deep, profound stillness of space. When we think of a black hole, our imagination conjures an image of perfect, absolute darkness. It is the universe's ultimate endpoint, a cosmic void from which nothing, not even a single particle of light, can ever return. For decades, this was our firm understanding. A black hole was a place where the laws of physics as we knew them seemed to break down, crushed under the weight of infinite gravity. We pictured its boundary, the line called the event horizon, as the universe's final one-way street. Anything that crossed it was lost forever, pulled into an unknowable center. A black hole, by its very name and nature, was a place of eternal clearness, a perfect shadow cast across the cosmos. It takes, it does not give. And then in the year 1974, a physicist named Stephen Hawking presented an idea that fundamentally changed our understanding of these dark giants. It was a revolutionary concept, one that seemed to defy logic itself. Hawking suggested that black holes were not in fact perfectly black. He proposed that they have a temperature, and if they have a temperature they must glow, even if it's just a faint cold whisper of warmth. And if they glow, they must be losing energy. He claimed that over immense, almost unimaginable stretches of time, black holes could slowly leak. They could shrink, they could eventually evaporate. This idea created a beautiful paradox. How can light escape from an object whose very definition is that it traps light? The answer lies at the turbulent border where two of our greatest scientific ideas meet. On one side, we have the physics of the very large, the smooth, predictable world of gravity, planets and stars. This classical view is what tells us the event horizon is a final, inescapable barrier. But on the other side, we have the physics of the very, very small. This is the strange, fuzzy and wondrous world of quantum mechanics. And in this world, the universe is never truly still. The rules are different. And most importantly, in the quantum world, empty space is not truly empty. Picture that vast, dark emptiness between the stars. To our eyes, it is nothing. But at the smallest possible scale, this vacuum is alive. It is a shimmering, restless sea of energy. We call it the quantum foam. From this sea, tiny pairs of particles are constantly bubbling into existence. They are called virtual particles. A particle and its opposite, an antiparticle, are born together, borrowing a tiny flicker of energy from the void itself. They exist for an impossibly short moment, a fraction of a second, so small we can barely comprehend it. Then they find each other, collide and vanish, returning their borrowed energy to the vacuum. This is happening constantly, everywhere. In the space between galaxies, in the room around you, and even in the space right at the very edge of a black hole. This restless sea of ghosts, this constant simmer of something and nothing is the key. It is the secret to how a black hole, the very definition of darkness, can learn to glow. For the longest time we believed black holes were the universe's ultimate prisons. They were seen as cosmic vacuum cleaners, points of infinite density, with gravity so powerful that nothing, not even light, could escape once it crossed the line. This one-way street concept was absolute. But Stephen Hawking showed us that the universe is far stranger and more subtle. The key to this cosmic puzzle isn't deep inside the black hole's center, but right at its absolute edge, a boundary we call the event horizon. To understand what happens here, we first have to understand nothing. In our everyday lives, a vacuum is just an empty space. But in the strange world of quantum mechanics, there is no such thing as true emptiness. The vacuum of space is actually a roiling, chaotic soup of energy, a quantum foam. In this foam, tiny particles are constantly flashing into and out of existence. These are not the permanent particles that make up you or me. They are virtual particles. They appear in pairs, a particle of matter and a matching particle of antimatter. They are born by borrowing a tiny bit of energy from the vacuum alone allowed by the universe's physics for an impossibly short amount of time. Before the universe's bank can notice the depth the two particles find each other, collide and annihilate, vanishing back into the nothingness from which they came. They repay their energy loan perfectly. This happens everywhere all the time in the empty space between you and this screen. Now let's take this bubbling quantum foam and place it at the most extreme location imaginable, the event horizon of a black hole. The event horizon isn't a physical wall you could touch or see. It is a boundary of information, a point of no return. It is the precise line in space where the black hole's gravitational pull becomes so strong that to escape you would need to travel faster than the speed of light. Since nothing can do that, anything that crosses this line is lost forever. It can only move in one direction, inward toward the black hole's center. This is where the magic happens. Imagine one of these virtual particle pairs pops into existence exactly on this dividing line. In a normal situation, they would annihilate each other and vanish in a fraction of a second. But at the event horizon, a catastrophe occurs. The gravity is so warped that the pair is torn apart. One particle, let's say the antiparticle, is created just inside the event horizon. It is trapped. It is pulled inexorably into the black hole. The other particle, its partner, is created just outside the horizon. It is still in the normal universe. The particle outside is now stranded. Its partner, which it needs to annihilate and repay its energy debt, is gone forever. It cannot be pulled back. The event horizon has permanently separated them. This lone escaping particle can no longer be virtual. It has been promoted. It becomes a real particle. To an observer far away, like an astronomer on Earth, it looks as if the black hole itself has just spat out a particle. This escaping particle has real positive energy, and it flies away into space. This steady stream of escaping particles, this flicker at the edge, is Hawking radiation. The black hole is glowing ever so faintly. But this creates a profound problem. Energy cannot be created from nothing. The universe is a very strict bookkeeper. If a real particle with positive energy just flew away from the black hole, where did that energy come from? It came from the black hole itself? This is the cost. To understand how, we must look at the unfortunate particle that fell in. Remember, the original pair was created with a total energy of 0, a balanced lone from the vacuum. If the escaping particle flies away with positive energy, the only way to keep the universe's books balanced is if the particle that fell in had negative energy. This concept is strange, but it's the only way to conserve energy. When this negative energy particle falls into the black hole, it acts like a debit. It subtracts its negative energy from the black hole's total energy. It's like adding debt to the black hole's mass energy account. And what happens when a black hole loses energy? Here we must turn to Albert Einstein's most famous discovery, E equals mc squared. This equation, where E is energy, m is mass, and c is the speed of light, tells us that mass and energy are two sides of the same coin. They are interchangeable. If the black hole loses energy by swallowing the negative energy particle, to pay for, there's one that had escaped it must also lose mass. With every single particle that escapes the black hole pays the price from its own being. It gets a tiny bit lighter. This means that black holes are not forever. They are slowly, painstakingly evaporating. This flicker at the edge is the black hole slowly dissolving back into the universe. However, we must understand the timeline. This process is slow on a scale that defies human imagination. For a large black hole, one with the mass of our Sun, or for the supermassive giants at the centers of galaxies, this evaporation is almost non-existent. The temperature of their Hawking radiation is astoundingly low, just a tiny fraction of a degree above absolute zero, the coldest temperature possible. Right now, the entire universe is filled with a faint leftover glow from the Big Bang called the cosmic microwave background radiation. This background energy bathes the universe in a heat of about 2.7 degrees above absolute zero. A large black hole is colder than this, billions of times colder. This means that at this current moment in the universe's history, large black holes are actually gaining mass, not losing it. They absorb far more energy from this background radiation and from nearby stars and gas than they are able to radiate away through Hawking's slow process. They are like ice cubes in a warm drink, and the drink is still warmer than the ice, and so it seems like a final goodbye. A one-way door. For decades this was the consensus. A black hole was a simple object, a place where information and matter went to die. It was a period at the end of a star's sentence. But physics, like the universe itself, cannot stand a true ending. It cannot tolerate an absolute disconnect. There was a deep problem, a conflict hiding in the shadows. On one hand, we had Einstein's great theory, general relativity. This is the law of the very large. It describes gravity, the graceful curve of space-time, the orbits of planets, and the immense smooth structure of the black hole itself. It is a theory of elegance and certainty. On the other hand, we have quantum mechanics. This is the law of the very small. It describes the chaotic, fuzzy, unpredictable world of atoms, electrons, and particles of light. It's not a world of certainty, but of probabilities. It's a world where empty space is not empty at all. These two great theories are the pillars of modern physics. They both work perfectly in their own domains, but at the event horizon of a black hole, these two worlds collide. Here you have an object with immense gravity, Einstein's world crushed into an infinitely small point, the quantum world. The two theories gave different conflicting answers about what should happen. Physics was broken, and then in the 1970s Stephen Hawking sat down to see what would happen. If you applied the strange rules of the quantum world to the edge of Einstein's black hole, he didn't try to solve the singularity, he just looked at the boundary, the horizon. What he found was not silence, he found a whisper. He found the bridge. This is the profound, beautiful meaning of what we now call Hawking radiation. It is the first and still the most important link between these two great pillars of reality. It proves that black holes are not disconnected. They are not separate. They are woven into the same fabric as everything else. To understand this, we must zoom in. Let's drift toward the event horizon, that smooth black edge. In the quantum world, the vacuum of space is a simmering, bubbling foam of potential. It is not empty. Tiny pairs of particles, a particle of matter and a particle of antimatter, are constantly bursting into existence. They are born from borrowed energy. In any normal part of space, they exist for an impossibly short moment before they find each other, annihilate, and pay back their energy loan. The universe is perfectly balanced. But what happens if this pair is born right on the razor's edge of the event horizon? Imagine two tiny dancers born in an instant. By pure chance, one dancer is born just inside the horizon and the other is born just outside. The one inside is trapped. It is pulled inexorably toward the singularity, its fate sealed. But the dancer left outside is now alone. It cannot find its partner to annihilate. It is stranded. This lone particle has a debt of energy it cannot repay. So the black hole itself pays the price. The black hole gives a tiny, tiny fraction of its own energy, its own mass, to this orphaned particle. This energy makes the particle real, and it floats away out into the cosmos. This escaping particle, this whisper from the edge, is Hawking radiation. This is the bridge. A quantum event, the particle pair was forced to interact with a gravitational event, the horizon. This radiation is the conversation between the two great theories, and this radiation has a signature. When you analyze the energy of these escaping particles, they have a perfect thermal profile. This means they have a temperature. This idea was a revolution. It meant a black hole wasn't a cold, dead object, it was a complex thermal system. This opened a whole new field of science, black hole thermodynamics. Just like a star or a cup of hot tea or a block of ice, a black hole follows the laws of heat and energy. It has a temperature. It has entropy, which is a measure of its information or disorder. This discovery proved that a black hole is not an end. It is a participant in the universe's grand exchange of energy. But here is the most curious part of the discovery. The temperature of a black hole is inversely related to its mass. This means a giant supermassive black hole like the one at the center of our galaxy, millions of times the mass of our sun, is actually incredibly impossibly cold. Its temperature is just a fraction of a degree above absolute zero, the coldest anything can possibly be. It is far colder than the background chill of space itself. Its whisper is so quiet it's almost silent. But a small black hole would be different. If a black hole with the mass of a mountain could exist, it would be warm. A black hole with the mass of a car would be searingly hot. And a tiny microscopic black hole would be a blazing inferno of energy. The smaller the black hole, the more violent its curve of spacetime at the edge, and the more hot its radiation. This leads us to the black hole's final ultimate fate, that escaping radiation carries energy. And as Einstein taught us with his most famous equation, energy equals mass times the speed of light squared, energy and mass are the same thing. When the black hole loses energy to that escaping particle, it must also lose a tiny, tiny, tiny amount of its mass. The black hole is evaporating. For the giant black holes we see today, this process is unimaginably slow. They are so cold and the universe around them is still relatively warm, so they are actually absorbing more energy from stray starlight and background radiation than they are losing. They are still growing, not shrinking. But let us travel forward in time, far into the future, trillions and trillions of years from now. The stars have all burned out, the galaxies have faded, the universe is a cold, dark, empty expanse. Now there is nothing left for the black holes to eat. The universe is finally colder than they are, and so their long fast begins. Slowly, particle by particle, they begin to lose their mass. The whisper of Hawking radiation carries their essence back into the void. For eons, this process is a slow, patient trickle. A supermassive black hole might take 10 to the power of 100 years to finally disappear. This number is so large our minds cannot even grasp it. But as it loses mass, it gets smaller. And as it gets smaller, it gets hotter. And as it gets hotter, it radiates faster. This is the runaway process. As the black hole shrinks, its evaporation accelerates. In its final millennia after an eternity of near nothingness, the black hole begins to warm up. As it shrinks to the mass of a planet, then a mountain, it begins to glow first a dull red, then a bright white. In its final second of life, the black hole has shrunk to the mass of a small asteroid, but it is blazing with the energy of trillions of nuclear bombs. It becomes a sphere of pure high-energy light, and then in one final brilliant flash of gamma rays, it is gone. The event horizon vanishes, the singularity ceases to exist. Everything that ever fell into it, every star, every planet, every particle of dust has been returned to the universe, converted back into its purest form, heat and light. The black hole, which we thought was a prison, was just a bridge. It was a way for the universe to store matter and energy to hold it in waiting, and then in the final quiet twilight of time to give it all back. It is the ultimate act of cosmic recycling. But this idea, this faint glow from the edge of nothing, it implies something even stranger. If a black hole has a temperature or warmth, however cold, it must also have a mess. In physics, we call this entropy. It is a word we use to measure disorder, or perhaps a better way to think about it is information. Think of your room. When it's perfectly clean, every book in its place, every object arranged is just so there's really only one way for it to be clean. It has low entropy, but a messy room. A messy room can be messy in a million different unique ways. The books can be on the floor, on the bed, under the chair, open or closed. It has high entropy, it holds more information about its many possible states. The universe, it seems, loves to move from order to mess. It's a fundamental law, perhaps the most fundamental. We call it the second law of thermodynamics. It is the relentless, irreversible march of things. A hot cup of coffee always cools down, spreading its warmth, its energy to the cooler air in the room. It never works the other way. The cool air never spontaneously gathers its heat and makes the coffee hotter. This one-way street is entropy. It is the reason we can break an egg, but we cannot unbreak it. The broken egg is a state of higher disorder, higher entropy. This law is the arrow of time, the reason we remember the past but not the future. For decades, this simple law created a terrible giant problem for black holes. A black hole, by its very nature, seemed to be a perfect destroyer. It seemed to be a cheat. You could take a burning star, a giant complex system buzzing with heat containing enormous entropy full of information, and throw it into a black hole. And poof, it would be gone. From the outside, the black hole would just get a little heavier, a little bigger. But the mess, the information, the star's entire complex history, it would all vanish, erased from the cosmos. This would mean the universe's most sacred rule, the second law of thermodynamics, was broken. And if that law could be broken, then everything we thought we knew about the universe was wrong. For a long time, physicists were truly stuck. But then in the early 1970s, a brilliant young graduate student named Jacob Bekenstein dared to ask a simple, profound question. What if the black hole doesn't destroy the information? What if it keeps it? He proposed that a black hole must have entropy of its own. When a black hole swallows that messy star, the black hole's own entropy increases by at least as much as the entropy it ate. The cosmic accounting book is balanced. The law is saved. This was a beautiful, radical idea. It implied that black holes must be hot long before Hawking proved how they could be hot. But it led to an even more difficult question. If the entropy is stored, where is it stored? And how much information can a black hole hold? Our intuition, our experience with the world, tells us that the amount of mess or information you can store depends on the space you have. It depends on volume. A bigger box holds more things. A bigger library holds more books. We live in a three-dimensional world. We naturally assumed a black hole's entropy would depend on the vast three-dimensional volume hidden inside its event horizon. Bekenstein, following the pure logic of the mathematics, discovered something that defied all intuition. It was a discovery that would shake the foundations of physics. He found that the entropy of a black hole, the measure of all the information it had ever swallowed, was not proportional to its volume. It was proportional to its surface area. Let that sink in for a moment. Not the three-dimensional space inside, but the two-dimensional boundary, the skin that separates it from our universe. The event horizon. This is one of the most profound and bizarre ideas in all of science. It's as if you could store a vast, sprawling library with millions of books not only inside a giant warehouse, but by simply writing all the information onto the outer walls of the building. It seems impossible. How can a flat, two-dimensional surface hold all the information of a three-dimensional world? This is where the idea gets its name, the holographic principle. You have seen a hologram perhaps on a credit card or a sticker. It's a flat two-dimensional piece of plastic that when the light hits it just right reveals a full three-dimensional object. All the information required to build that three-dimensional image is somehow encoded on the two-dimensional surface. The black hole Bekenstein and his successors realized is a hologram. It suggests that everything that has ever fallen into that abyss, every galaxy, every sun, every forgotten particle, every single bit of history is not lost in the crushing singularity at the centre. Instead, all of its information is perfectly preserved. It is translated, encoded and stored on the two-dimensional surface of the horizon itself. Think of it as the universe's ultimate storage device. The hard drive on your computer stores information using tiny magnetic regions. A black hole does the same, but its pixels are the smallest possible unit of space allowed by the laws of physics, an area we call the Planck area. It is a square with sides that are just 1 Planck length, long, a number so small it is a 1 preceded by 35 zeros after the decimal point. The surface of the event horizon is tiled with these impossibly tiny pixels. Each one acts like a single bit of information storing a 1 or a 0. When a star falls in the black hole doesn't just gain mass, its surface area grows just enough to create new pixels on its surface, new storage space to write down the complete description of the star it just consumed. Nothing is ever truly lost, it's just recorded. The sheer capacity is bottomless. A single black hole the mass of our sun could hold more information on its surface than all the data stored on Earth multiplied by a trillion times. It is the most compact, most dense, most efficient information storage system imaginable. It is a beautiful and terrifying thought that the darkest object in the universe, the symbol of absolute destruction, is actually the universe's most perfect preservation system. It is a cosmic vault. It forces us to reconsider what reality even is. The black hole was the first clue, a hint that our three-dimensional world might itself be a projection, an illusion, a hologram painted on a distant boundary. So when you look up at the void, at that patch of perfect darkness where a black hole might be, you are not looking at an ending. You're looking at a library. You're looking at a surface that contains perhaps the most information packed into any single place in the cosmos. A silent hidden order, a cosmic memory held in the dark, waiting just at the edge of sight. So we've journeyed to the edge of the event horizon, and we've found that black holes are not the eternal prisons we once thought. They leak. Thanks to the strange rules of the quantum world, they radiate. They glow ever so faintly with what we call Hawking radiation. Over unimaginable stretches of time, they lose their mass, they shrink, and eventually they must vanish. This realization, this slow evaporation, is profound. But it also presents us with a crisis, a deep, unsettling conflict between the two great pillars of physics. This is known as the black hole information paradox, and it is perhaps the most difficult puzzle in modern science. To understand this, we must first appreciate a central rule of our universe. In the quantum world, the world of tiny particles that governs all matter, information is shared. It cannot be created, and it absolutely cannot be destroyed. This is a fundamental law, perhaps the most fundamental. It's a principle we call unitarity. What does this mean? It means that if you have complete knowledge of an object, you can in principle track its history and predict its future. The information is always preserved. Think of it like this: if you burn a book, you might think the information inside it is lost. You can no longer read the words. But in physics, the information isn't gone. It has just been scrambled. It's been transformed. The information of the paper and ink now exists in the exact composition of the smoke, the ash, and the heat that radiated away. A perfect physicist with a perfect supercomputer could theoretically gather every particle of smoke, every bit of ash, and trace their paths backward to reconstruct the original book. The story is not erased. It is merely encoded in a new chaotic form. This principle is the bedrock of physics. It ensures that cause leads to effect, that the past connects logically to the present. Without it, the world is not predictable. It becomes magic. Now let's return to our book. Instead of burning it, we drop it into a black hole. The black hole grows a tiny bit heavier. The information of that book, its unique arrangement of atoms, the story it told, is now trapped inside beyond the event horizon. According to quantum mechanics, that information must still exist somewhere. Perhaps it's scrambled on the black hole surface, or perhaps it's hidden deep within the singularity. But it must be somewhere. Here is the crisis. The black hole begins to evaporate. It emits Hawking radiation. When Stephen Hawking first did the calculations, his results showed that this radiation is thermal. This is a crucial word. Thermal means it is random, it is generic. It's a faint chaotic glow whose only properties are determined by the black hole's overall mass, its spin, and its charge. It doesn't care what fell in. The radiation from a black hole that ate a library of books would look identical to the radiation from a black hole that was only formed from pure hydrogen gas, as long as their mass was the same. The radiation in Hawking's original calculation is dumb. It carries no specific information about the unique items that the black hole consumed. It is a featureless statistical hiss. This leads us to the 10,000-word question, the one that has kept physicists awake for decades. What happens at the very end? The black hole radiates and radiates and radiates. It shrinks, getting smaller and smaller, hotter and hotter, until in a final tiny flash it disappears completely. It evaporates. So, where did the information go? Where is the story of our book? Where is the information about the massive star that collapsed to form the black hole in the first place? It cannot be inside the black hole because the black hole is gone. It does not seem to be in the Hawking radiation that came out because that radiation was thermal and random. The information, it seems, has been fundamentally erased, vanished from the universe. This is the paradox, and it is a nightmare. It creates an impossible conflict. On one hand, we have quantum mechanics, the foundation of all modern physics, which insists with no exceptions that information cannot be destroyed, it must be conserved. On the other hand, we have Hawking's calculation born from the marriage of general relativity and quantum theory, which suggests that black holes evaporate and do destroy information. They are the universe's ultimate deletion key. One of these fundamental ideas must be wrong, or more likely our understanding of them is deeply incomplete. If information can truly be lost, then the entire structure of physics as we know it collapses. It means that if you fall into a black hole, your past is not just inaccessible. It is erased from the universe's memory. It means the universe itself is forgetful. It means that at a fundamental level, the universe is not logical. The past does not uniquely determine the future. This is a possibility so profound, so unsettling that most physicists cannot accept it. This is the fire that rages at the intersection of gravity and the quantum world. This is the search for the ashes of the black hole, the subtle encoding that must carry the stories of everything that ever fell inside. The universe we believe does not forget. We just haven't learned how to read its memory. This simple, elegant and terrifying idea that black holes evaporate was not just a new chapter in physics. It was a crisis. It lit a fire, and the resulting argument would be called the Great Debate. It was a battle for the very soul of physics, and it began with Stephen Hawking himself, who stood firmly on one side. His initial position was as bold as it was terrifying. He claimed that the information was indeed truly lost. Think about what that means, not just scrambled, not hidden, but deleted from the universe. To you and me, that might sound acceptable. Things get lost. But to a physicist, this is heresy. The most fundamental rule of quantum mechanics, the law that governs everything at the small scale, is that information is never lost. This principle is called unitarity. It means that if you have perfect knowledge of an object now, every atom, every spin, every vibration, you can, in theory, know its entire past and its entire future. Let's use a simple analogy. If you burn a book, the information seems lost. The words are gone, turned to smoke and ash. But a perfect physicist could in theory capture every single particle of smoke, measure the heat, track every bit of ash, and from that scattered data reconstruct the entire book. The information is just scrambled, distributed across the environment. It is not gone. Hawking was saying that the black hole is different. It is the one place in the universe that doesn't just scramble the book. It erases the story permanently. If this were true, it meant our most trusted rulebook quantum mechanics was wrong. It meant the universe was not a perfect logical system. It meant that at its core, reality itself had a leak. This set the stage for a decades-long conflict. Physicists, most notably Leonard Susskind and Gerard Hooft, could not accept this. They believed the universe must make sense, that information must be conserved. The battle lines were drawn. If information wasn't lost, where did it go? Several alternatives were proposed, each more strange than the last. The first idea was, what if the information doesn't get out? What if as the black hole evaporates over trillions of years, it shrinks and shrinks, but it doesn't disappear completely? What if it leaves behind a tiny microscopic remnant? A speck smaller than an atom containing the entire library of information for everything that ever fell in every star, every planet, perhaps even a source. This idea sounds convenient, but it creates even worse problems. How could a single tiny particle possibly hold the information of an entire galaxy? That's like trying to store all the data on the internet in a single grain of sand. It just doesn't work. The amount of information an object can hold is supposed to be related to its surface area. A tiny remnant would have almost no surface area. This idea just traded one paradox for another, and it quietly faded. The second alternative was much more promising. Maybe the information does escape. Maybe it is carried away by the Hawking radiation. Hawking's original calculation showed that the radiation was random thermal, like the gentle, meaningless hiss from a warm object. But what if he missed something? What if the information is still there, not in the individual particles but hidden in the relationships between them? Imagine the information as a very, very long and complex sentence. Hawking looked at each word, each particle of radiation and said, "This is just random noise." But maybe the secret isn't in the words themselves, but in the subtle correlations, the pattern. Maybe the meaning is held in the relationship between the first particle emitted and the billionth particle emitted. The information isn't broadcast, it's woven into the fabric of the escaping radiation in a way that is impossibly complex to decode. This seemed like the right path. Information is scrambled, not destroyed. Quantum mechanics is safe. But then physics found an even deeper problem. A problem at the very heart of how the radiation is created. This is the real sharp edge of the paradox. Settle in, as this is the core of the mystery. It has to do with quantum entanglement. You may have heard of this. Einstein called it spooky action at a distance. It's a connection between two quantum particles. When they are created as a pair, they are linked. They are one system, even if they are separated by a galaxy. If you measure one and find it is spin up, you instantly know the other is spin down. Their fates are tied together. Now think about the event horizon. Hawking radiation is created when a pair of particles is born from the quantum foam. One particle falls in the black hole and the other particle escapes. The escaping particle is the Hawking radiation. Because these two particles were born as a pair, they are entangled. The escaping particle, let's call it particle A, is forever linked to its partner particle B that fell into the black hole. This is their connection. Quantum mechanics has a very strict rule about this entanglement is monogamous. A particle can only be fully entangled with one other partner. Here is the crisis. If the information from the astronaut who fell in years ago is also supposed to escape, it must be encoded in the new radiation that is leaving today. This means particle A, the escaping one, must also be entangled with the information of that astronaut. So particle A is now entangled with two things. It is entangled with its partner, particle B, inside the hole, and it is entangled with the old information, the astronaut, that it is carrying away. This is a quantum impossibility. It is a violation of the monogamy of entanglement. Physics had cornered itself. Either information is lost, Hawking's original terrifying idea. Information escapes, but to do so it violates the fundamental rule of entanglement, the monogamy problem. Or something else is happening. Something violent. Some physicists propose that to break this illegal second entanglement and a massive wall of fire, a firewall must exist at the event horizon, instantly burning up anything that tries to cross. The debate was at a standstill. It was a choice between three impossibilities. The gentle, quiet surface of the black hole had become a battlefield. And to find the answer, physics would have to look not at the black hole itself, but at the very nature of space and reality, leading to an idea that perhaps our whole universe is just a projection. But this victory, this wonderful idea that the black hole's story is written in the steam, it led us to a place that is darker and stranger and far more terrifying than the simple loss of information. It led us to a contradiction so profound that it threatens to break either quantum mechanics or Einstein's gravity once and for all. It begins with a simple, beautiful and very strict rule in the quantum world, a rule that we call the monogamy of entanglement. It's a lovely word, monogamy. And in this case it means almost exactly what you think. It is a law of quantum accounting. A particle, let's call her Alice, can be profoundly completely entangled with another particle, Bob. Their fates are one. If you measure Alice, you instantly know the state of Bob, no matter how far apart they are. Their connection is total, but this rule states that Alice cannot at the same time be equally and completely entangled with a third particle, Charlie. She can have a casual weak connection to Charlie, and a casual weak connection to Bob. She can be weakly entangled with many different things, but she only has a limited amount of entanglement to give. If she is fully married to Bob, she has no connection left to give to Charlie. She cannot be maximally entangled with two different things at once. It is a fundamental limit. One particle, one perfect all-in connection. That's the law. Now, hold that thought. The monogamy of entanglement. Let's go back to our black hole. It's not young anymore. It is very, very old. It has been evaporating for billions, perhaps trillions of years. It is now just a shadow of its former self. Most of its mass has been radiated away as this cloud of Hawking radiation, this steam. And according to our new understanding, this cloud of steam contains the story. The information of the astronaut, the star, the encyclopedia, it's all there delicately encoded in the connections between all the particles in that steam. A new little piece of radiation, a new particle escapes from the black hole. Let's call it the latecomer. For the universe's story to make sense, for information to truly be saved, this new latecomer particle must be connected to the past. It must be entangled with all the radiation that came before it. It has to be part of the same story. If it's not, the information is still scrambled, still lost. So requirement number 1. The escaping particle must be entangled with the early radiation that's already out there. But wait, where did this latecomer particle come from? It was born just moments ago, right at the event horizon. It was created in that quantum fluctuation. As one half of a pair, it has a twin, a partner, a particle that fell inside the black hole. To be created as a pair, they had to be entangled with each other. That is how they are born. They are two halves of one whole. Their connection is the very definition of their existence. So requirement number 2. The escaping particle must be entangled with its twin inside the hole. Do you see the crisis? Our little latecomer particle is being asked to be fully married to 2 different partners at the same time. It must be entangled with its twin inside the black hole, and it must also be entangled with all the radiation outside the black hole. It is being asked to violate the monogamy of entanglement. Quantum mechanics throws up its hands and says, this is impossible. This cannot happen. The math breaks. This is the paradox. We call it the Amps paradox after the 4 physicists who proposed it, or more commonly, the firewall paradox. Because the solution they proposed is a nightmare. They said, okay, the laws of quantum mechanics are absolute. Monogamy is the law. The particle must be entangled with the outside radiation to save information. Therefore, it cannot be entangled with its twin inside. But it has to be. They were born as a pair. No, they said. What if the moment that pair is created at the horizon, that instant, the bond, the entanglement between them is violently broken? This act of breaking a quantum entanglement, this fundamental connection, it's not a gentle separation. It doesn't just not happen. It requires an incredible, a catastrophic amount of energy. This energy from the constant breaking of these pairs billions of times a second all over the surface of the black hole, it would build up. It would create a new region of space right at the event horizon. It would create a wall, a barrier of incandescent high-energy particles, a firewall. This isn't a metaphorical wall. It is a physical barrier of pure energy hotter than the center of a star sitting right at the edge of the black hole. This firewall solves the information paradox. It breaks the core connection, allowing the particle to be monogamously entangled with the outside radiation carrying the information away. Quantum mechanics is saved, but it creates a new and perhaps even worse nightmare. It destroys Einstein. It destroys perhaps the most beautiful idea in all of physics, the equivalence principle. Einstein's happiest thought was that gravity is not a force, it is a curve in the fabric of space-time. And if you're falling freely, in a spaceship with the engines off or in an elevator with the cable cut, you feel perfectly weightless. You're in a local inertial frame. And he promised that falling into a large black hole would be uneventful, gentle, smooth. Because you are in free fall, you would feel no force. You would float across the event horizon, that imaginary line, and you wouldn't even know. You wouldn't feel a thing. You would be blissfully unaware that you had just now passed the point of no return. It would be a peaceful local experience. The firewall takes this beautiful, gentle idea and burns it. It says that at the moment you, the astronaut, drift gently toward the horizon, you do not float. You are not peaceful. You are annihilated. You are met by this wall of unimaginable energy and instantly reduced to your fundamental unentangled particles. There is no smooth crossing, there is no uneventful passage, there is only the fire. So this is the choice. This is the crisis at the heart of modern physics. To save quantum mechanics and the conservation of information, do we have to build this terrifying wall of fire at the horizon? And in doing so, do we tear down the gentle, smooth geometry of Einstein's universe? Do we sacrifice Einstein to save Planck? We are stuck. We are caught between our 2 greatest descriptions of reality. We have followed our logic, and it has led us to a place where we must choose between a black hole that scrambles information or a black hole that burns you alive at its border. The paradox has only deepened. The calm, dark, simple void has been replaced by a raging quantum inferno. And as we drift here, in the quiet, we wonder, what fundamental, simple truth are we still missing? What have we overlooked in the fire and the night? And so we drift forward carrying this profound and unsettling mystery of the black hole. Let's just pause here for a moment. Feel the quiet of this thought. We have travelled far from the gentle dance of nebulae to the very edge of an event horizon, a place where reality itself seems to tear apart. And in that extreme place we found a clue, a thread. Do you remember back in our third meditation we discussed the work of Jacob Bekenstein and Stephen Hawking? We learned that a black hole has entropy, a measure of its hidden information. We learned that when a star, a complex and beautiful object, collapses, all the information about what it was is not destroyed, it is stored. But the part that truly baffled physicists, the part that still makes us catch our breath, is where it is stored. Logically, we would assume this information, this entropy, would be proportional to the black hole's volume. An object with more three-dimensional space should hold more information. If you have a bigger box, you can put more things inside it. But that is not what Bekenstein and Hawking found. They found that the information is proportional to the black hole's surface area. It scales with the two-dimensional boundary, the event horizon itself. Think about that. All the information needed to describe every particle, every quantum state, every memory of the massive three-dimensional star that died, it all fits perfectly onto the two-dimensional surface of the whole. The inside story is written in its entirety on the cover. For decades, this was seen as a strange property of black holes, curiosity of extreme gravity. But then in the 90s, physicists like Gerard Tooft and Leonard Susskind began to ask a question so audacious it threatened to rewrite our entire understanding of reality. The question was this: if a black hole is the most information-dense object the universe can possibly create, a limit for reality, and its information is stored on a two-dimensional surface, then what if this isn't just a rule for black holes? What if this is a rule for everything? This is the birth of the holographic principle. It's an idea that sounds like pure science fiction, but it emerges directly from the mathematics. Let's think about a hologram. Not the universe, just a simple hologram you might find in a museum or on your credit card. It's a flat two-dimensional piece of film. It looks like a meaningless scramble of light and dark patterns. But when you shine a specific kind of light on it, a full three-dimensional image appears to float in space. You can walk around it, see it from different angles. It has depth, it has form. All the information required to build that three-dimensional object is completely encoded or scrambled onto the two-dimensional surface of the film. The holographic principle suggests that our universe works the same way. The principle proposes that everything we see, this room, the stars, the galaxies, all of this complex three-dimensional reality is nothing more than a projection. It suggests that the fundamental film of our universe is a distant two-dimensional boundary, and we are the hologram. It suggests that what we call space and volume might not be fundamental at all. They might be emergent properties, an illusion of depth created by information stored on a flat surface. This would mean that the total amount of information in our entire vast universe is not determined by its three-dimensional volume but by the area of some great cosmic boundary far, far away. This idea is dizzying. It's one thing to say it, but how could you ever prove it? How could you show that a universe with gravity like ours is just a projection of a flatter universe without gravity? This is where the story takes a brilliant turn. In 1997, a physicist named Juan Maldacena discovered a mathematical bridge, a dictionary that did exactly this. It is called the ADES-CFT correspondence, which stands for Anti-de Sitter Conformal Field Theory. Let's not worry about the complex names. Let's focus on the idea. It is beautiful. Maldacena imagined a specific kind of toy universe. This universe has a bulk or an inside which is called anti-de Sitter space. Think of this as a universe in, say, 5 dimensions. It has gravity, it has space-time that curves, and it even has things like black holes. It's a complete gravitational system, much like our own. But this universe has an edge, a boundary, and on that boundary lives a completely different theory, a conformal field theory. This theory lives in 4 dimensions, the boundary of a 5-dimensional space. It is a quantum theory full of particles and fields buzzing around, but it has no gravity at all. What Maldacena proved with stunning mathematical rigor is that these 2 theories are equivalent. They are dual to each other. This means that any question you ask about the complex gravitational universe inside the 5-dimensional anti-de Sitter space can be perfectly translated into a question about the simpler non-gravitational quantum theory on the boundary, the 4-dimensional conformal field theory. And it works both ways. A very difficult problem in quantum physics on the boundary, like how particles interact, can be solved by translating it into a much simpler problem about gravity and the bulk, like an object falling. This was the first concrete mathematical example of the holographic principle in action. It showed a universe with gravity emerging like a hologram from a flatter universe without gravity. The two were just different descriptions of the exact same underlying reality. One is the 3D projection, the other is the 2D film. This correspondence changed theoretical physics overnight. It provided a new tool, a Rosetta Stone, for translating the two great pillars of physics. It connects Einstein's theory of gravity with the theory of quantum mechanics. It suggests that the very fabric of space-time, the stage we've been talking about, is not fundamental. It is woven from the quantum entanglement of particles living on a distant boundary. So let this thought wash over you as you rest. What does it mean to be real? Are we the actors on the stage, or are we the patterns projected from the film? The holographic principle tells us we might be both. It redefines our place in the cosmos. We are not just living in a universe, we may be the expression of a deeper, simpler, flatter code. The laws of physics, the story of time, the existence of space itself, all projected from an unfathomable distant shore. We are perhaps a beautiful, complex thought written on the boundary of reality. We have reached a point of deep conflict. On one side, we have the unshakable laws of quantum mechanics, which insist that information is permanent and can never be truly destroyed. On the other side, we have black holes, which, according to our best understanding of gravity, are perfect information destroyers. When a problem in physics is this fundamental, it often means our entire view of reality is wrong. The solution that has emerged is perhaps the most profound and mind-bending idea in modern science, the holographic principle. What is a hologram? You have probably seen one on a credit card or a driver's license. It is a flat two-dimensional surface that contains all the information needed to project a complete three-dimensional image. The holographic principle suggests that our entire universe might be just like that. It proposes that the three-dimensional reality we experience with its depth, its stars and its galaxies is a projection. It's an image generated from a set of physical laws and information encoded on a distant two-dimensional boundary at the very edge of the cosmos. This boundary is the true source code of the universe. The physics that happens on this boundary is a complete quantum theory, and in that quantum theory, information is always without exception conserved. It's a basic rule. This idea introduces a powerful concept called equivalence. It means that the complex three-dimensional world inside, which contains gravity and black holes, and us, is just a different way of describing the simpler two-dimensional world on the boundary, which does not have gravity or black holes. They are like two different languages telling the exact same story. Now let's apply this radical idea to our paradox. We have two descriptions of the same system. The boundary description. A two-dimensional quantum system with no gravity. In this system, information is always saved. It's a fundamental law. The inside description, our three-dimensional world with gravity and black holes. Because these two descriptions are equivalent, because they are just two different ways of telling the same story, they must agree on the most basic facts. If the boundary theory must conserve information, then the inside theory must also conserve information. If this equivalence is true, the information paradox simply cannot exist. It dissolves. It becomes a non-question. Information must be soon saved. So where does the information go? The holographic principle provides a stunning answer. When something like a book falls into a black hole, it doesn't truly enter and disappear in the way we imagine. Instead, as it approaches the point of no return, the event horizon, all the information that makes up the book, the arrangement of its atoms, the data on its pages, gets smeared out and encoded onto the two-dimensional surface of the event horizon itself. You can think of the event horizon as a giant cosmic hard drive. The information never actually makes it inside, it stays on the surface. The inside of the black hole that we imagine is just a holographic projection of that data stored on the horizon. This completely changes our understanding of Hawking radiation. The radiation is not random. It is created at the event horizon precisely where all the information is stored. As the black hole evaporates, the escaping radiation particles are not blank. They are subtly and in an incredibly complex way imprinted with the information stored on the horizon. As the black hole shrinks, its event horizon gets smaller. The information stored on it is forced out, scrambling itself into the escaping radiation. By the time the black hole is completely evaporated, all of the original information that ever fell in has been slowly and meticulously leaked back out into the universe, encoded in the quantum patterns of the radiation. The information is saved. It is never lost, just very, very scrambled. This powerful holographic idea has led physicists to an even deeper and stranger connection. It is an idea summarized in a simple but world-changing equation ER equals EPR. Let's break that down. EPR stands for Einstein-Podolsky-Rosen, which is the scientific name for quantum entanglement. This is the spooky action at a distance that links two particles. If you measure one, you instantly know the state of its partner, even if it's on the other side of the galaxy. ER stands for Einstein-Rosen, which is the scientific name for a wormhole. A wormhole is a theoretical tunnel or bridge through spacetime connecting two distant points like a shortcut. The equation ER equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena, suggests that these two things are the same phenomenon. It proposes that any two particles that are entangled are in fact connected by a microscopic wormhole. The spooky link is the tunnel. This has an incredible implication for our black hole. Remember our pair of entangled particles at the horizon? One particle escapes becoming Hawking radiation and the other, its partner, falls inside. These two particles are entangled. According to ER equals EPR, this means they are connected by a wormhole. This paints a new breathtaking picture of a black hole. It suggests that the very fabric of the space-time interior of the black hole is not a separate dead-end space. Instead, the inside is woven from the vast network of all these tiny wormholes. The inside is built from its entanglement with the outside. The black hole's interior is fundamentally and physically sewn to the radiation that is escaping it. In this view, the information isn't inside or outside. The information is the connection. The inside of the black hole and the radiation that has left it are not two separate systems. They are two ends of the same reality linked by a tapestry of quantum entanglement that manifests itself as space-time. The paradox is resolved because the inside and the outside were never truly separate to begin with. We have been sitting with this puzzle, this deep and cosmic contradiction. A book, a star, a memory falling into a black hole in the universe, forgetting that it ever existed. It felt wrong, didn't it? It felt like tearing up the most fundamental rule of existence, the law that information, that the essence of what something is, can never truly be destroyed. For decades we stared at Stephen Hawking's equations. They said the radiation flowing out of a black hole was pure random empty heat. But the defenders of quantum mechanics, they held the line. They insisted the information must get out. We just don't know how. They needed a map, not a map of space, but a map of information, a way to track it. This map has a name, the Page Curve, named for the physicist Don Page. It is one of the most important theoretical graphs in all of modern physics. Imagine the black hole is a slow, steady bonfire, and the information is a secret written on a piece of paper that you've thrown in. Hawking's original idea suggested the smoke coming off the fire is just smoke, meaningless and random. But the Page Curve is a prediction, a different story. It says, let's measure the entropy of that smoke. Entropy is just a beautiful scientific word for how much we don't know. It's a measure of randomness, of hidden information. At first, as the black hole slowly burns, the radiation does look random. The entropy goes up, our ignorance increases. The smoke seems meaningless. This is the first half of the journey. The black hole is just hoarding secrets. But then the Page Curve does something profound. It predicts that exactly halfway through the black hole's life, when it has evaporated half of its mass, the curve must turn. It must bend and the entropy must start to go down. Why? Because the universe must keep its promises. If the entropy goes down, it means the smoke is no longer random. It means the new wisps of smoke are deeply quantum mechanically connected, entangled with the smoke that came out billions of years earlier. It means the secret is being pieced back together. The radiation is purifying itself, the information is coming home. This was the great hope. For decades, this was just a prediction. Hawking's math never produced this curve. His math showed the entropy just going up and up and up forever, straight into oblivion. We had a map but no path. This is where the story gets truly strange. This is the breakthrough from just the last few years, a solution so bizarre it challenges our very idea of where things are. To solve this, physicists had to change the rules of the game. They were trying to calculate the entropy of the radiation, the smoke far, far away from the black hole. They ran the equations and they kept getting Hawking's answer. The information was lost, until they tried something that sounds like madness. They realized the only way to get the Page Curve to bend, the only way to make the math obey the laws of quantum mechanics, was to add a new piece to their calculation. When they were calculating the properties of the radiation outside the black hole, they found they also had to include a region deep inside the black hole. Think about that for a moment. It's as if you were trying to measure the total temperature of your bedroom, and the only way to get the right answer was to also include the temperature of a specific single rock on the moon, as if they were part of the same system. This region inside the black hole, this piece of the puzzle, they gave it a humble name. They called it the island. This isn't just a clever metaphor, it is a profound mathematical discovery. It means that the island, a piece of the black hole's deep disconnected interior, is somehow the same. It is mathematically identical to the radiation that is billions of miles away. The information that fell in our book, our memories, doesn't just exist inside the black hole on that island. It also exists outside the black hole, encoded in the subtle entanglement, the hidden connections within the Hawking radiation. This breaks our minds because it breaks one of our most cherished common sense ideas, the idea of locality. Locality is simple. It's the belief that an object can only be in one place at one time. It's the belief that to affect something you have to touch it or be near it. The chair you are sitting on is here, the moon is there. They are separate. This new island prescription says no. It says the universe is non-local. It says the information inside the event horizon and the information outside in the radiation are not two separate things. They are two descriptions of the one same thing. So where is the information? It's on the island and it's in the radiation, both. This is the solution. It saves information. It avoids the fiery wall of energy at the horizon. The book is not burned. The memory is not lost. It escapes not by climbing out, but because the universe is connected in a way we never ever imagined. The deep interior of that dying black hole is the radiation we catch with our telescopes. We are left with a new, deeper and perhaps more unsettling reality. To save the laws of quantum mechanics, we had to admit that space itself is not what it seems. We had to accept that here and there might just be an illusion, a stubborn habit of our perception, and that deep inside the darkest object in the cosmos, there is a connection, a hidden bridge that reaches all the way back out to the stars and to us. So we are left with this staggering, beautiful and deeply unsettling idea that black holes are not forever, that they shine even if it's with a light born from the quantum shadows, that they have a temperature, a life and an eventual death. This is the legacy of Stephen Hawking, a concept so profound it ties together the three great pillars of physics, gravity, quantum mechanics and thermodynamics. It is perhaps the single most important clue we have about the true unified nature of reality. And yet, there is a quiet puzzle at the heart of it, a simple, frustrating question. If this radiation is real, where is it? Why have we never ever seen it? We point our most powerful telescopes at the giants in the night at Sagittarius A star, the supermassive beast at the heart of our own galaxy, or at the famous Cygnus X1, and we see nothing. No gentle hum of radiation, no glow, just the void screaming in its silence. The answer, it turns out, is a matter of scale. The math that predicted the glow also gave us its temperature, and the temperature of a black hole is inversely proportional to its mass. This means the bigger the black hole, the colder it is. And the black holes, we can see the ones born from dead stars, are massive. A black hole with just the mass of our sun would have a temperature of only about 60 nanokelvins. That is 60 billionths of a degree above absolute zero. This is impossibly profoundly cold. It's so cold that it presents the first great problem for our hunt. Our universe, you see, is not at absolute zero. It is filled with a bath of ancient leftover light from the Big Bang. We call it the cosmic microwave background. This background radiation has a temperature of its own, about 2.7 degrees Kelvin. Now compare the two. The black hole is billionths of a degree. The universe around it is almost 3 whole degrees. This means that for every tiny particle of Hawking radiation the black hole whispers out into the cosmos, it is absorbing billions and billions of particles from the cosmos. It's like trying to spot a single, faintly glowing ember in the middle of a roaring blast furnace. The black hole isn't radiating heat away, it's absorbing it. The stellar mass black holes we see are not evaporating. They are not shrinking. They are in fact still growing, feeding on the leftover warmth of creation. The whisper of their own decay is completely and utterly drowned out. We will not see these black holes die, not for trillions, not for quadrillions of years, until the universe itself has expanded and cooled so much that the cosmic microwave background is colder than they are. This is a deep disappointment. It feels as though nature has hidden its most beautiful secret just out of reach. But what if we are looking at the wrong black holes? The theory says that to find a hot black hole we need to find a small one, a very, very small one. We need a black hole with the mass of a mountain or an asteroid. But a star cannot make a black hole that small. When a star collapses, it has a minimum amount of mass required to overcome the forces holding it together. The black holes born from stars are all by default large and therefore cold. So where could a tiny black hole come from? To find the answer, we have to rewind the clock all the way back Not just before the stars, but before the galaxies, before the atoms. We must go back to the first fractions of a second of the Big Bang. The early universe was not the calm, ordered place we see today. It was a churning, chaotic impos, jobly dense soup of energy and quantum fields. In this primordial chaos, the universe was not smooth. It was lumpy. Some regions were slightly denser than others. In most places, the explosive pressure of the Big Bang smoothed these lumps out, letting the universe expand. But what if in some tiny, unlucky region the density was so extreme that the sheer force of its own gravity overcame the universe's expansion? In that first instant, that tiny, overdense patch of energy wouldn't have become a star. It would have collapsed directly, instantly into a black hole. This is a primordial black hole. These are black holes not born from death, but forged in the very crucible of creation itself. And because they weren't formed from stars, they could have any mass. Some could be as massive as a galaxy. Others could be as small as a grain of sand. And here at last is our hope. Let us imagine one of these primordial black holes. Let's say it was formed with the mass of a large mountain or perhaps a small asteroid about 1 billion tons. For the last 13.8 billion years, it has been drifting through the cosmos. And because it is so small, it is hot. Far, far hotter than the cosmic microwave background. It has not been absorbing energy. It has been evaporating. For billions of years, it has been steadily losing mass, leaking its energy back into the universe, shrinking, getting smaller and smaller. And as it gets smaller, it gets hotter. And as it gets hotter, it radiates faster. And as it radiates faster, it gets smaller even faster. You see the feedback loop. For most of its life, it was a slow, steady leak. But as it nears the end, the process becomes a runaway catastrophe. The evaporation accelerates, spiraling out of control. In the last few minutes of its life, it's glowing with the brightness of a star. In its final second, the black hole is no longer a black hole ATC all. It is a blinding point of light, hotter than a supernova. And then in the last instant, with all its remaining mass, it explodes. It vanishes in a final brilliant flash of high-energy particles and radiation. The whisper we have been hunting for at the very end of its life becomes a scream. This final scream, this last gasp of a dying primordial black hole would be a burst of some of the highest energy light in the universe, gamma rays. This is the signal we are hunting for. Somewhere out there in the dark, a tiny relic from the Big Bang might be taking its final breath right now. The hunt is on. Telescopes like the Fermi Gamma Ray Space Telescope are not just looking for colliding neutron stars or exploding supernova. They are also patiently scanning the skies, listening for a sudden orphan burst of gamma rays coming from nowhere, signifying nothing except an end. A flash of light with a very specific energy signature that flares up and then vanishes forever without any afterglow. That would be the smoking gun, the definitive proof of Hawking radiation. So far, we have found nothing. The sky remains silent. This lack of a signal is in itself a powerful piece of data. It tells us that these small evaporating black holes, if they exist, are very, very rare. It places limits on how many of them could have been created in the Big Bang. The hunt in the cosmos continues. But what about here on Earth? We cannot see the real thing. But perhaps we could build an analog. This is one of the most clever and beautiful ideas in modern experimental physics. If we can't get to a real black hole, maybe we can test the principle of Hawking radiation in a laboratory. After all, what is the key ingredient? It's not actually the gravity. The magic ingredient is the event horizon. It's the existence of a boundary, a point of no return that separates the inside from the outside and creates the quantum particle pairs. So the question becomes, can we create an event horizon for something else? Imagine a river. The water is flowing and it's speeding up as it approaches a waterfall. Now imagine a fish. This fish can swim at say 5 miles per hour. Upstream, where the water is flowing slowly at 2 miles per hour, the fish is fine. It can swim upstream back and forth. It can send messages or perhaps sound waves back and forth to its fish friends. But as the river flows, it gets faster. 2 miles per hour, 3, 4, and then it reaches a point. The point where the water itself is flowing faster than the fish can swim. The water is flowing at 6 miles per hour. Once the fish crosses that line, it is trapped. No matter how hard it swims, the current is pulling it backward. It cannot by any means get back upstream. It cannot even send a sound wave upstream because the sound wave, like the fish, is dragged backward by the flow. This fish has crossed a horizon. For that fish, it is a point of no return. This is an analog black hole. Or as the scientist who proposed it, Bill Unruh, called it a dumb hole, because sound or phonons, which are particles of sound, cannot escape. Hawking's mathematics predicted that this horizon, this sonic watery horizon, should also radiate. It shouldn't radiate light, of course, it should radiate sound. It should have a sonic Hawking temperature releasing tiny quantum pairs of phonons. This is a testable idea, and so in laboratories around the world, scientists set out to build them. Not with water and fish, but with things far more precise. They used light. In a special optical fibre, they sent a powerful laser pulse. This pulse changes the properties of the fibre as it moves, creating a hump that other weaker light particles get caught on. It creates an event horizon for light. They used sound. They created a waterfall of atoms in a tiny ultra-cold system and measured the sound waves trying to escape. And most successfully, they used something called a Bose-Einstein condensate. This is a bizarre state of matter, a cloud of atoms chilled to just a fraction above absolute zero, where all the atoms lose their individual identity and start to behave as one single massive superatom. It is a perfect quantum pure silent medium. In this superatom, scientists used lasers to create a flow carefully accelerating the fluid until at one precise point it was moving faster than the speed of sound in that medium. They had created a perfect controllable tabletop sonic black hole, and then they listened. They looked for the telltale sign of Hawking radiation, the linked pairs of particles, one inside the horizon and one outside. In 2014, and then with more precision in 2016 and the results came in. They saw it. They measured the quantum correlations exactly as Hawking's math had predicted. They found the thermal signature. They had measured the analogue of Hawking radiation. Think about that for a moment. In a lab in a tiny puff of gas colder than deep space, we have heard the echo of a black hole's whisper. Now, this is not a real black hole. This experiment does not prove that gravitational black holes in space must radiate, but it proves that the mathematics works. It proves that the physics of a horizon, when combined with the rules of quantum mechanics, does produce radiation. It gives us profound confidence that Hawking was right. The hunt continues on two fronts. We are staring at the heavens waiting for the final violent flash of an ancient dying traveller. And we are here on Earth in darkened labs, creating tiny fragile horizons in fields of light and sound, probing the mathematics of the edge. We have not yet captured the whisper from space, but we have learned how to create our own. We have seen the principle in action, and this confirmation, this analogue, only makes the original puzzle more profound. Because if black holes do radiate, if they do shrink and die, then we are faced with the greatest paradox in all of physics. A puzzle that threatens to break everything we think we know. What happens to all the things that fall in our journey has taken us to the very edge of reality, to the darkest objects in the cosmos. We have stared into the abyss, into the singularity, and we have listened for the faint quantum whisper of their slow evaporation. And now we find ourselves back in the quiet, back in the stillness of our own minds, asking a final simple question. What does it all mean? What are black holes really? After all this exploration, we can see they are so much more than just cosmic vacuum cleaners. They are not just dead stars. They are perhaps the most profound objects in the entire universe. They are the ultimate laboratory. Laboratories. They are mirrors. Think of a mirror. A mirror shows you your own reflection. A black hole does something similar, but instead of reflecting our faces, it reflects the state of our knowledge. It reflects the boundaries of what we are capable of understanding. When we look at a black hole, we see the place where our two greatest ideas about the universe collide and break. On one hand, we have Albert Einstein's theory of general relativity. This is the grand, beautiful theory of the very large. It describes gravity as the elegant curving of space and time. It paints a picture of planets waltzing around stars, of galaxies spinning in a cosmic dance. And it works perfectly. It predicts the orbits of planets and the bending of light with incredible precision. On the other hand, we have the theory of quantum mechanics. This is the strange, fascinating theory of the very small. It describes the world of particles of energy of uncertainty. It tells us that reality at its most basic level is not a smooth picture, but a fuzzy, shimmering collection of probabilities. And this theory also works perfectly. It powers our computers, our lasers, and explains the very fire inside the stars. For a century, these two theories have lived in separate houses. One rules the large, the other rules the small. But at the heart of a black hole, in that infinitely dense point called the singularity, the two are forced to meet. Gravity becomes impossibly strong on a scale that is impossibly small. And our theories fail. They give us answers like infinity, which is nature's way of telling us we have asked the wrong question, or that we are missing a vital piece of the puzzle. This is what we mean when we say a black hole is a mirror. It shows us this fundamental contradiction. It reflects the limits of our genius. A black hole is a signpost in the cosmos that points and says, beyond this your maps are wrong. A new theory is needed. The quest for a theory of everything, a single set of rules that can describe both the quantum and the cosmic, begins right there at the event horizon. And so this journey we have been on, this quest to understand the black hole, is revealed to be something much deeper. It is not just an astronomical problem. It is a journey to understand the very fabric of reality. It is a quest to understand what space and time truly are. Are they fundamental? Are they just an illusion? A black hole, by bending and breaking them, forces us to ask. It is a quest to understand information. We believe in our bones that information cannot be destroyed. A thing cannot simply vanish from the universe. And yet the black hole seems to do exactly that. The information paradox. This deep contradiction is not just a technical problem for physicists. It asks us, what is the universe made of? Is it made of matter and energy, or is it at its deepest level made of information? The black hole sits at the centre of this debate, a silent guardian of the answer. And yet for all their violence, for all their mystery, we find a strange and profound order. We find a quietness. We have returned to this idea again and again. The chaos of a star's collapse gives way to an object of perfect simplicity, described by only 3 numbers: its mass, its spin, and its charge. The terrifying finality of the event horizon gives way to the slowest, most gentle process in the cosmos hawking radiation. This is the most powerful lesson of all. It seems that even here at the absolute extreme of nature, there is no true chaos. There is only a deeper, more subtle set of laws. The universe does not descend into madness inside a black hole. It simply begins to follow new rules, the rules of quantum gravity. These are the beautiful, intricate laws that we are only just beginning to decipher. It suggests a universe that is at its core rational and profoundly elegant, even in its most terrifying creations. So we end our journey where we began, in the quiet darkness. We look up at the night sky at the scattered points of light, and we now know what hides in the shadows between them. We know about the gentle curves in space-time. We know about the hum of quantum fields. We know that the most powerful objects in creation are also the most simple, and that their deepest secrets are whispered, not shouted. Our place in all of this is small. We are tiny, brief creatures on a speck of dust orbiting an average star in an average galaxy. But we have a remarkable ability. We can look out and we can listen. We can build theories and we can tell stories. We are the part of the universe that has woken up trying to understand the rest. This is the gift of the black hole. It is a mirror that shows us our limits, but it is also a doorway that invites us to step beyond them. It teaches us that the greatest truths are often found in paradox. It shows us that even in the heart of the deepest darkness, there are laws, there is elegance, and there is a profound, subtle beauty. Our journey is to simply be still, to be patient, and to listen to its whispers.